organizers for the invitation. I think this is actually a fairly important enterprise, and I'm actually quite happy to be involved in it. Seth's comment yesterday about how we actually distinguish or find good interactions from bad interactions and to identify the things that actually make the difference got me thinking a little bit last night, and at least I can sort of think two ways in which these sorts of interactions can take place. In the first example, I imagine that the mathematician essentially plays the role of the bartender. So the geophysicist goes to the bar and brings his problems. He presents the problems to the bartender, who nods sympathetically and provides a little bit of advice, and then the geophysicist goes back to work with those suggestions and actually hope to make some progress. In order for that to be kind of a useful interaction, though, there has to be some new wrinkle or some new angle that actually brings out new math that will entrain the mathematician into sort of more productive collaboration. And so there's sort of an element of hope in that context. I think the other way that this could happen is that the mathematician or statistician has a new idea or a new result and would like to test it and thinks that geophysics or geosciences is a great test bed for testing out these ideas. And so again, he would perhaps go to earth scientists, ask for suggestions about how this could be done, and hopefully these will provide good examples for the mathematician, but hopefully be some important transformation or improvement in the geosciences. And so the point, I guess, that when we're thinking about this institute, what we have to try to do, I think, is to try to reduce the amount of hope that's required to make useful collaborations. And so somehow there has to be an umbrella of important overarching problems, but there also has to be some role in terms of connecting the right people, in terms of doing the right problems. And so I was sort of thinking, while you guys served me a drink, I was thinking about actually explaining this problem of, just flip back for a sec, this problem of planetary dynamos. It's in some ways a relatively new problem in the way that the first successful models probably started to appear a little bit over 10 years ago. And I think in many ways the original techniques and approaches and strategies that we've used in these models have kind of come to their natural end. And we're really, in terms of making progress, looking at alternative strategies and alternative approaches, and so it may in fact be a fruitful area for collaboration. So from the point of view of a geoscientist, there's a couple of things that I could comment about this problem. The first is that it's an intrinsically interesting problem. Dynamics is quite interesting. It has a lot of complexity, a lot of interesting features, sometimes very unintuitive features. But I think also from a planetary science point of view, it's actually quite important. And the reason is that the existence of a magnetic field in a planet is a very sensitive diagnostic of the internal dynamics. In the context of our own solar system, only the Earth and Mercury have present-day magnetic fields. Neither Venus nor Mars have them at present, although Mars appears to have had one in early times. And the point is that by understanding the conditions under which magnetic fields can be generated, we're going to learn an awful lot about the internal dynamics of planets and probably a little bit about their evolution. And so this might be relevant perhaps in the long term because it's one of the things that you can at least observe from space, the presence of a field that could actually tell you something about the internal dynamics of a planet. So perhaps down the road when we're exploring extrasolar planets in greater detail, this might be a tool that we would look to try to peer inside. So the plan for this talk is to just give you a brief outline, sort of a context, the scene set for the problem, talk about the physical description of the problem and some of the challenges that we're facing and some of the things that we're trying to do to get around these problems, but then come back at the end and focus on the opportunities where I see for collaborations. Okay, so we think that the magnetic field of the Earth gets generated in a liquid metal core that's in sort of the inner half, at least in the Earth, and probably all the terrestrial planets have this more or less structure. It's probably iron alloy, and the viscosity of this liquid is probably a little bit less than water, so it's very, very fluid. It has, in the Earth's case at least, a solid inner part, which is just simply a consequence of the fact that the core is cooling, and it freezes in the center, the hottest place first, just simply by virtue of the pressure dependence of the phase diagram. Now, the processes that actually are responsible for this are illustrated schematically here. So the overlying rocky mantle, which sits up here, draws heat from the core. This can produce cold thermal boundary layers at the top, which will drive flow. It will also cause the core to cool and solidify, and as you grow an inner core, there's latent heat released, which is an important source of buoyancy. But we also know from seismology that this isn't pure iron. It has alloys and other things dissolved into it that make the density less. And it also appears that some of those light elements get excluded when it freezes. And so we have an important source of compositional buoyancy, and these sources of buoyancy collectively drive flow and ultimately power the magnetic field. Now, this is one of the early models, Gary Glatzmeyer and Paul Roberts in the mid-90s. And it was really quite a remarkable accomplishment. I think if you were to ask both of those guys today, do you think this is the sort of thing that's going on in the core, I think that they would both probably acknowledge it's probably not even close. But it was proof of concept, it was possible to do, and the question then is, how do you go about making these models better? And so part of the issue is, what are the real challenges? And so I just wanted to walk through the equations. Like everyone that does fluid mechanics, you have a momentum balance, which you use to evolve the velocity field. And there's a bunch of forces that operate. These are rotationally dominated flows, like the atmosphere and oceans. So Coriolis plays an important role. The flows are mostly driven by buoyancy and often mostly resisted by the presence of magnetic fields. And we have this very small viscous term on the back. Now, if you were to sort of look at the relative importance of these terms to get a sense of what the nature of the dynamics is, you could look, for example, at the ratio of viscosity to Coriolis. And that number, by virtue of this being very, very small, is on the order of 10 to the minus 16 or so. These calculations that Gary was doing were probably 10 to the minus 3 or something on that order. So we're orders and orders and orders of magnitude away. Really, the best calculations now are still over 10 orders of magnitude away from where we should be. The way that this is usually rationalized or justified or maybe explained is the idea that, well, these flows, because of the low viscosity, are clearly going to be turbulent. And maybe what's really important is putting in the appropriate turbulent viscosity, which may in fact bring these into more realistic range with what we're actually running. But the point is that if you look at the importance of, say, the inertial effects relative to the Coriolis terms, and you put in some reasonable numbers, these are tiny. These are very, very small terms. And so if turbulence exists in these calculations, it's a very different kind of turbulence than what we normally think of in the atmospheres or in sort of classical homogeneous turbulence. So we really then have to question what sort of eddy viscosities or parameterizations of this parameter are we actually thinking about in these models. Okay. The induction equation is essentially based on Maxwell's equations. It's really Maxwell's equations in a low frequency limit. All the pieces actually existed before Maxwell put this all together, but it essentially relates to the change in the magnetic field as a part of two terms. One is an induction, the effect of the fluid velocities acting on the magnetic field to regenerate this field, and then persistent ohmic losses, which are constantly causing the field to diffuse and decay away. And the thing that makes this problem actually practical and in future presumably solvable is the fact that this ratio of this production relative sort of to the scales at which this dissipation takes place are not so big, 1,000 or so. These are the sorts of things that we probably can do now and will certainly be able to do better in the future. So if we can get the velocities right, in essence, we can solve this problem. The heat equation or the compositional equation, if the buoyancy is compositional, is governed by an equation like this. The diffusivities in general are very, very small. And importantly, the ratio of the, say, thermal diffusivity relative to the magnetic, sometimes called the Roberts number. You put in viscosity to diffusivity, magnetic diffusivity, sometimes called the magnetic Prandtl number. These are very, very small. And what that means is that the length scale of the temperature perturbations or the length scale of the velocity perturbations are really small compared with the length scales that you expect in the magnetic field. And so this creates a real challenge. I think people often in this community talk about how important it is to get the Ekman number right. I suspect that this is the real serious problem. In fact, in most models, if you want to get the dynamo to look more like the Earth, you make this number bigger than 1 rather than smaller than 1. So it's, again, a problem that there's still things in the models that we really don't understand. Okay. Well, this is just an example to illustrate what these solutions look like. This is a recent model that was done by Hiro Matsui, who's working with me at Berkeley. What it shows is the vertical vorticity in one of these calculations, and it's I'm going to rotate it here so you can have a look. Rotation is a very, very strong effect in these models, and what you're going to see is this thing rotated around. You see the sort of Coulomber structures. These are essentially anticyclones or cyclones, essentially. They're not exactly columns, as you often see it described in sort of cartoons, more like sheets. I'll just show that again. But again, very fine scale structure, cyclones, anticyclones, elongated in the direction of the rotation axis by the strong effects of rotation. So this is a conceptual model of how we think the model actually works. This is from a very nice and recent review article by Chris Jones in Annual Reviews of Fluid Mechanics. So here he's got sort of a schematic of these cyclones and anticyclones, and each are associated with a secondary flow. So for example, the cyclones will have flow down toward the equator into the anticyclones and back up toward the boundary. And it's the interactions of these sort of cyclonic flows plus the secondary flows that are responsible for generating the Earth's magnetic field. So as an example, if you were to start out with a line of field, say in the northern hemisphere, which wrapped around a line of latitude, how do you convert that field into a vertical field which would give rise to the dipole component? Well, the idea here is that the secondary flows will essentially transport the magnetic field. So if you're in a cyclone, this downward flow will carry that initial field in this direction. Similarly, if you have upwelling flows in this column, you'll have this field being carried up. So this region in between, you'll get a region where the vertical component of the magnetic field is positive. Okay? But then right next to it, you'll have a region where the magnetic field is negative, pointing down. And so the idea here is that these columns, if you'll see this region here, will advect this positive magnetic field in toward the center. This region here, which is negative, is actually going to be transported out. So the combination of the secondary flows and generate the field, the cyclonic flows essentially separate the positive and negative parts. You push the positive part to the inside, you push the negative parts to the outside, and you get something that looks like this. This is a picture of the vertical component of the magnetic field. You can see the positive parts are accumulating on the inside, the negative parts are being pushed to the outside, and eventually ejected out of the convecting region of fluid. So let me just run this simulation for you, or this model result for you. The thing that you notice about this is you can again see all of the concentration of the vertical component of the field, the part that contributes to the dipole, collecting in the inside, but you'll also probably notice that the scale is much larger than it was for the velocity field. And this is for a Roberts number or magnetic Prandtl number of only about 1/2. So just a very small change, and you already start to see these effects in terms of the differences in the scales. This is another recent result. This is actually probably as good as we've seen in the literature published. A number, Ekman number of 10 to the minus 3. So viscosity to Coriolis effects about part 10 to the 6th. You see the velocity field, in particular the radial component at the equator, and the corresponding magnetic field that flow produces, much larger scale. We're only 0.1. So we really need to go many more orders of magnitude down in scale, and sort of the extremity of this scale separation is going to become stronger, stronger, stronger. Okay. So the way that we've tried to attack this problem is using at least the framework of large eddy simulations. It doesn't actually provide the solution for you, but I think what it does do is provide a good framework for thinking about what the problem actually is. And so for those who haven't seen this before, if you have a true field, then you can only represent the field on a finite grid, then you can only resolve the large-scale features, of course. And you can think of that process as representing the field on your grid as taking the true field, spatially filtering it so that you can actually resolve this feature. And so the filter function in this particular case, a Gaussian, would have a width which would be on the order of your grid spacing. And so the idea is that you're not solving the Navier-Stokes equations or the temperature equations. What you really want to solve is the filtered version of those equations. And so the challenge lies in casting this equation in terms of the quantities which you can actually resolve on a grid. So the first step that is always done in this procedure is to interchange the orders of the derivative operators and the filtering operators. And as long as the filter function is a constant width, then this is perfectly fine. If it changes width, then this is not allowed, and you have to introduce corrections for it. But that's relatively straightforward. We understand how the error arises, and we think that we can make estimates for it. The real challenge essentially is taking this term and then representing it in terms of the fields that you can actually resolve on the grid, and then introducing this correction term, which is the piece that you want to add to the equations to account for the subgrid scale effects. And it's just simply the difference between the term that you should be using for the heat flux versus the term that you actually use. So it just accounts for the missing correlations that exist at the small scales. Now, for the dynamo problem, it turns out that there are 4 of these terms. We have a heat flux terms, a momentum flux or a Reynolds stress terms, and these are conventionally represented in the dynamo models in terms of eddy diffusivities or eddy viscosities. But we also have Maxwell stresses, interactions of small-scale magnetic fields, or interactions of velocity fields and magnetic fields, which can give rise and contribute to the large-scale part of the solution. What was interesting, actually, is these have never been considered or not considered currently in dynamo models. And certainly some of our early work with Cartesian models suggested that these terms actually were a little bit larger, in fact, than these. Okay. So the idea behind an eddy diffusion model is to say that we can represent this term with a term that simply depends on the gradient in the large-scale temperature field, where the coefficient, the thermal diffusivity is some product of the velocity scale and a suitable length scale for the eddies that you're intending to represent. And so if you take this and stick it into those equations, you just simply get a temperature equation in which the thermal diffusivity has been enhanced, which is essentially what we're doing in the numerical models. One of the things that you can do is you can actually try to test these ideas to sort of see how well this works. And one thing that I'll come back to a couple of times is the fact that if I were to run really resolved calculations on a grid where I could actually capture all the scales, in principle I should be able to calculate this term on a grid which was much coarser than the one that I ran the calculations on, and then come back and actually test some of these ideas. So you can't run numerical models with properties that are actually realistic, but what you can do is you can take a small part of the core and actually run simulations with the correct estimates of the parameters and see what sort of structures and behaviors you actually get in this small cube. And so this is an example of what you get when you do that sort of thing. This is the box here again. And again, I'll just sort of emphasize that the vertical component will be aligned with the rotation axis. The gravity vector, where it points, will depend on where I am, whether I'm at the equator or the pole, and then I'll impose some large-scale magnetic field which pervades this whole conducting fluid. So that's the picture of the model. Here's the rotation axis. Here's the gravity acting. In this particular calculation is at mid-latitude, so that this gravity vector sort of points roughly at a 45-degree angle in this plane here, and there's an imposed magnetic field. And this is the temperature structure that you get from those calculations. You see that the temperature anomalies tend to be fairly elongated in the rotation axis direction. That's the Proudman-Taylor effect again. And it was sort of seen in the large-scale numerical simulation as well. You also tend to get large scales in the direction of the magnetic field just simply because the flow doesn't want to distort and bend the magnetic fields. The field resists, and so it tends not to produce small scales in that direction. But in the perpendicular direction, there's actually no resistance, really, except for viscous effects to producing small scales. And you get very, very small scales developing, sort of plate-like or essentially plate-like eddy structures. So the core at small scales probably looks a little bit like this. The interesting thing about the process that actually sets the scale in this particular calculation is not viscosity, but actually thermal diffusivity. So that as you bring thermal anomalies hot and cold together, diffusion essentially erases them long before they sense viscosity. So in fact, the viscous dissipation that actually takes place in this calculation is almost zero. There's almost no viscous dissipation at all. So the point is, if you're going to use eddy diffusivities to represent this effect, then the way in which the energy flows through your calculation is going to be very, very different from the way it actually works in nature. The other point to make is that if you wanted to sort of characterize these flows in terms of an eddy diffusivity, you're going to have it be very anisotropic. It's going to have to depend on direction, and the strength of the anisotropy is going to be affected by things like magnetic fields, so it's going to be a complicated thing to try to parameterize. Okay. So one of the strategies that we've tried to use to do this is something called the scale similarity method. This is sort of a picture of the velocity scale, or think of it as the square root of your kinetic energy as a function of wave number. You decide where you're going to truncate your grid, and this is the part that you'll resolve, and this is the part that you're going to toss away. And the strategy essentially is to actually take the resolved solution and filter it, so that you have now some solution which is on a coarser grid, effectively, obtained by filtering the part which was on the resolved grid. And so the idea here is that you're going to approximate this true subgrid scale flux, in this particular case the heat flux, with a term that looks like this. And maybe the way to think about this is just imagine, instead of applying this filter to the grid, the fields that we're actually resolving, imagine you applied that to the true fields. So this would be V and T, no squib, no wiggles, but just simply this overbar and these overbars here. That would be the true subgrid scale heat flux on this coarser grid. And so what we're basically saying is that we can make an estimate of what the subgrid scale heat flux would be on this coarser grid, but using fields that only extend to this limit rather than going all the way down to the small scale. And then to make the argument that on the true scale, the true subgrid scale that we want to account for, this one here, that it's basically similar, essentially identical, but different in terms of amplitude. And there's sort of strategies for dealing with how you estimate those coefficients, which I can show you if you're interested. The point is that it's nice in a variety of ways. First off, if your solutions that you're resolving are very anisotropic, then you'll capture that anisotropy in your subgrid scale models. Plus also it's fairly easy to construct models for, say, Maxwell stress or the induction, where the form of the subgrid scale model would maybe not be so clear as in the case of an eddy diffusion model, for example. Okay. Well, you can actually look at what these terms actually do in numerical models to see how they do, to see whether it makes any sense. What's being shown here is the subgrid scale terms. So the Reynolds stress or the momentum flux, the Maxwell stress, and the induction term. And what's shown here is the fact that the work that's done by these subgrid scale terms can be both positive and negative. So in the regions where these terms are positive, what that really means is that the subgrid scale model is pumping energy into the large scales. In the case where the work is negative, that's basically taking energy out of the resolved scales, which would be what you'd expect for a eddy diffusion model. So an eddy diffusion model could never give you a situation where you're actually pumping energy. It can't happen. We can come back, though, and I'll show you in just a sec, that in fact these features are exactly what you'd expect for these sorts of numerical models, that the subgrid scales, in fact, can pump energy back into the large scales. Maxwell energy is taking energy out, so it's acting like a friction term, and the SGS, the induction terms, is a mixed bag. Some of it's taking it out, in other cases it's actually pumping energy back into the small scales. So again, the solutions actually have fairly complicated dependencies and fairly complicated spatial dependencies. What I'm showing you here is just actually an attempt to see whether those results made any sense. It's comparing a coarse-grained subgrid scale models with a very fine-grained solution. We can actually evaluate the subgrid scale models exactly to see how well they're doing. And this just simply shows the spatial correlation, one being that we have good spatial correlation and clearly hatched marks if we're actually negatively correlated. You see, it's not perfect. There are regions where we don't actually do a very good job, but we generally do a pretty good job with these schemes. If you do exactly the same thing with an eddy diffusion model, what you actually find is over most of the space, you're actually negatively correlated. So in some ways, it'd be better to do nothing. But in fact, the numerical models would actually be unstable if you did nothing. So essentially, our eddy diffusion models have nothing to do with physics and everything to do with just stabilizing the numerical scheme. So it's probably not what we want to do. Okay. So let me just now return to the challenges where I think opportunities may exist. And I say brute force will probably not achieve the desired results. You can say with absolute certainty that we'll never get the actual numerical results or appropriate parameters for the core. But what we might be able to do is with brute force get to the point where at least these solutions are asymptotically similar to the Earth's actual case, and then do appropriate scaling. But it's not clear that we're there yet. So what do we need? We need better turbulence models, and I put turbulence in quotes here because, again, it's very strange turbulence where the inertial effects don't play a large role in actually the dynamics of this turbulence. It's almost all buoyancy driven. What I've shown you is that filter-based closures with no physics, just simply saying what happens at the smallest scales probably also happens at the scales that are off my resolution, can in fact capture the anisotropy and backscatter, but there's a limit to how far these effects can actually take. We've been able to get solutions that successfully produce the large scale on grids that are about 3, maybe 4 times coarser in all 3 dimensions than the fully resolved calculations. It's not clear that we're going to have to be able to go much further than that. In terms of parameters, we can probably go maybe a couple of orders of magnitude better in Ekman number, but that's about it. So if we want to do better, we're probably going to have to do something a little bit more sophisticated, physics-based models, perhaps models that explicitly exploit this scale separation, which, if successful, would be good because the assumptions that underlie the scale separation actually only get stronger as we get closer to the real solution. And so, in fact, it may be possible to find simpler models as we get closer to the truth. In terms of efficient use of parallel computing, these methods really have to be adapted to the dynamics. We find that with the strong effects of rotation, very little variation in the direction of rotation axis. We want a grid that reflects that. In terms of other structures, we know a lot about the structures in these solutions, internal shear layers, etc. We know where they are. We can anticipate them. We don't necessarily need AMR, but we do need the ability to adapt grids that are specifically designed to dynamics, and then have solvers that can specifically deal with these unusual geometries. The problem that we face in terms of the domain is we're really dealing with all of space. We have to solve a potential field that exists everywhere outside the core. And if we're not going to use spherical harmonics, which is a very natural way to deal with the potential field outside the core, then we have to make sure that the methods that we choose don't allow energy to be leaking in from infinity to influence our solutions. And finally, we require very long simulations. Typically, these simulations require time steps, many time steps over the course of a day, and not simply if we dealing with sort of treating various forces implicit. Implicit treatment of Coriolis force, for example, doesn't really substantially reduce the time steps. And yet we want simulations to run over hundreds of thousands of years. We want to look at magnetic reversals or statistics of magnetic reversals. We need very, very long simulations and are required to take very, very short time steps. So better numerics is going to be a key part of making more progress. There are also current and planned missions to collect enormous amounts of magnetic field observations. And how do we go about actually using these things? A number of workers have talked about data simulations. I see these mostly as being used to quantify model shortcomings rather than making predictions about what the field is likely to do. But there's absolutely no question that the models that we have today are completely inadequate for describing the short-term dynamics. So we need better models that are more carefully constructed. The existing models are largely ad hoc, and there's really need for more formal asymptotic analysis. And then finally, the idea of introducing sort of intermediate complexity models to characterize these short dynamics is clearly an area where we're going to see a lot of progress, hopefully, in the next few years. With that, I think all. Thanks.
Yeah, I was wondering if you could comment. Oh, sorry. Grady Wright at Boise State University. I was just curious on if you could comment on the numerics that were used for some of those simulations or the dominant schemes that are used now.
Right. So the standard approach that's usually used is spectral method. The rationale for this is that, of course, there's great accuracy in terms of your spatial derivatives. Very natural way to treat the potential field outside, but it really does require you to fix your resolution. So, for example, in these simulations, we expect shear layers to form at the outside margin of that central inner core. How do you get the resolution that you need there without imposing the same resolution everywhere? Spectral model doesn't do it for you. The results that I showed in terms of those simulations that I was talking through with me today doesn't done with finite element in the sphere. Again, the grid really needs to be adapted specifically on the geometry. Tools are required. Maybe another way to sort of think about it is geometry defined by dynamics. And yet we have these spherical boundaries that you have to deal with. Potential field, which is spherical geometry. We have this boundary layer. It's often thought we sort of compatible with geometry needs to sort of mix together these models. But if we could do it, right, in terms of vertical structures, for example, I would guess that 40, 50, 60 point vertical versions are probably all we need. In the horizontal direction, So we're not going to do sort of spectral method. You're not going to do the cube sphere to do something specific. I'm interested in Bayes' functions as my concern about it, and maybe the comment is that I never get a feel in terms of how I can anticipate the world. Improve the resolutions and change the shape functions. So there does seem to be some work in the improbable to develop this. There still seems those techniques require more progress and more work.
I'd say certainly they're not as developed as spherical harmonics or finite elements yet. So, but you can expect accuracy, I guess, on the order of spherical harmonics types of things.
The question is predictability, right? So I've seen papers, where you change the shape functions, some of these basis functions, and error changes quite a lot in ways that you wouldn't expect. And so how do I know in advance in solutions that I don't have solutions that I can test against whether or not what I've chosen is a good choice or a bad choice? And so the advantages of the other techniques is that the foundations are there for me to know in advance what to expect. And it's the difference. Right. No, that's graded basis functions just don't have. Yeah. So it's kind of a, someone described this as sort of one of these things you have to have an intuition about.
Well, we do have that in some cases, like for vortex method we have it, right? But not for everything, every way you might use radial-based functions.
Abraham Solomon, your parameterization for eddy diffusivity seems pretty simplistic. Have you know, advances have been made in atmospheric motion science for more sophisticated ways of parameterizing eddy diffusivity that are intrinsically anisotropic and respect the intrinsic structure of the velocity field. Have you considered using? You know,
well, in some sense, sure, you could do that. But I think what's clear right here is the fact that if you were to use an eddy viscosity model, you wouldn't get this structure. And that structure is clearly there, right? So an eddy diffusion model will never pump energy back into the big scales from the small scales. And that's clear. I'll bet it's not done by parameterization. I'll bet it's not done by parameterization.
Well, you parameterize it and you just go diffuse, parameterize momentum, diffuse momentum.
Right.
Diffuse something like potential vorticity.
Right. So this is actually the Reynolds stress of the small scale flow that we've tossed away, driving essentially. This is essentially driving the jet. This is exactly the same as the things that you get in Jupiter, for example. You know, helical convection columns, they get tilted a little bit, they drive the jet. This is what's happening at the small scale, and these are what these schemes are actually able to pick up. So it's actually pretty good. I think going to an eddy diffusion model is more complicated also because it's going to depend on the rotation direction, it's going to depend on the direction of gravity, it's going to depend on the direction of the magnetic field and the intensity of that magnetic field. And so if you want to get all those things right, sure, maybe you could do it. I think that a physics-based model is probably the way that we're going to go in the long run, but I would be surprised if it's in the form of an eddy diffusion model. But you know, it's an area where this field actually needs to improve. The point I guess also I'd make is that what we're doing presently is just constant eddy diffusivity models that are constant across the whole core, right? And what you can see right here is that you'd be better to do nothing than that.
You know, you mentioned at the beginning that today Gary Glatzmeyer and Paul Roberts might sort of smile at that. So what would you say are the major advances that have been made since that pioneering?
Yes, I would say certainly the resolution calculation. Resolution that calculations can be run at. So, and that's just an advance in brute force computer power. And in terms of results, well, okay, so what have we learned? Yeah, it's a fair point. I guess I would probably turn that question around a little bit and say, what did we learn from Gary's and Paul's calculation? They probably won't like me saying this, but I think what we learned from those calculations that it was feasible to do. But I think those calculations were completely irrelevant from the point of view of the Earth. So I think we learned nothing about how the magnetic field was generated. So now we have a model where the convection columns, the structure of the convection columns are completely different, but they're more similar to some of the features that we see in existing magnetic fields. So I guess what I would say is we have models that look a little bit like, that produce field structures that look a little bit like the field that we see at the Earth's core mantle boundary. We see strong flux patches in high latitudes which are compatible with these convection columns, which you never saw in sort of area pulse simulations. What's surprising, though, is just because they're so far away from being realistic, I'm not 100% sure that we're getting results that look reasonable for the right reasons. So, you know, we get strong dipolar fields. These fields will reverse sporadically. What's actually been hard to get is dipolar fields that also reverse. So we're getting results that look pretty reasonable. They give us sort of temporal variations that look like some of the statistical fluctuations that we can get from paleomagnetic observations. So there's a lot of, what's that? Oh, you get westward drift. It's not purely westward. But the point is that you can get a lot of attributes that look similar to the observations, and yet it's really surprising, I guess. And so my feeling, I guess, and I'm probably not as enthusiastic about these results as some people you'll quote, but I think that we're still in proof of concept. And I think the idea of comparing these models to the Earth and actually learning something yet is still a ways off. But there are others who disagree with me.
So business of the hierarchy of models. I mean, are you saying that you don't trust necessarily these things that much more than Cook and Roberts or Chilkis and Potrel?
Well, look, I mean, these things are solving a dynamo problem, right? And so there's no question that all of the interactions are there. So maybe one thing that was surprising, to come back to this, I would have thought that probably a lot of the early dynamo work was based on the notion that the helical convection was the thing that converted the so-called, to go technical, toroidal field to the colloidal field, and that the differential rotation would actually play a big role in doing the opposite conversion. That turns out to be not the case in these models. The helical column does everything, for example. So that was a surprise. Is that the strengths of the fields are actually relatively weak, not so strong. That was a little bit of surprise. What's also true about these models, if you turn off the magnetic field, the flow doesn't change, which tells you that we're not there, I think. Because if viscosity is really playing almost no role, and you turn off the one of the two things that can break Proudman-Taylor, and the flow doesn't change, then it tells you that the one other thing is doing it. And you think that other thing is probably unimportant. And in the numerical simulations that I showed in the small cube, viscous dissipation plays no role. 99.99% of the energy is going into electric currents. Virtually none of it goes into viscous effects. So clearly there's something not right. But I think still we've come a long way in terms of getting closer.
This is maybe unfair to say so, but do you have any feel about what these new Mercury results are telling us? And I know that's probably too soon.
Yeah, it's going to be really fascinating. I think Mercury is unbelievable that Mercury has field.
Yeah. I mean,
so if you were to ask me, will Mercury have field in advance of Numerical and subsequently Mesmer said those changes.
Right. Well, having said, we've told that to classes repeatedly that it wouldn't have a magnetic field.
It does. Actually, the other thing that's true is to move defective fields again, which is even more defective. So there are a lot of things that we don't understand about these systems, and they seem to be more robust and able to operate than we would have might have guessed. The problem with the terrestrial planet, I didn't mention, but I probably should have. The reason why it's so useful as a diagnostic of internal dynamics is that metals have good thermal conductivity. And you have to, in order to cool, metals have good thermal and you have to, in order to cool, drive all these processes to the rocky part. And to get the heat out of the core, the mantle, the rocky part, actually has to take the heat out. It turns out, actually, that the in this sort of schematic picture here, for our typical estimates for how much heat this rocky part draws out of the core is not so different from the amount of heat that the core can conduct. And the point is, so if you don't have, for example, plate tectonics, which is very effective at cooling the planet, this heat flux goes down a little bit, and now suddenly you can supply all the heat that you need to the mantle by conduction. There's no point in convection in the dynamo. So the opportunity to get or not get a magnetic field in a terrestrial planet where you have this getting heat out, getting it out through a rocky shell, is kind of the thing that makes this a really interesting dynamic about the internal state of the entire planet. Not just the dynamo. Sort of not just the dynamo.
The last question got me to the other. Are we in a position to say much yet about the conditions under which a magnetic field will die? And I mean, does it have to? We don't have to wait. Do we have to wait for the core to completely solidify for the magnetic field to die, or what? I'm thinking Mars.
So the argument about Mars is it live fast and die young, and so that it cooled quickly, lost its heat, and then the vigor of convection in the mantle over top of it just decreased to the point where it shut this off. Where does that happen? When does it happen? We really don't know exactly.
Perhaps not so much in terms of magnetic field dynamics, but in terms of planetary dynamics.
Yeah.
I think understanding something about that would be really
right. So, for example, if you're looking out at extrasolar planets, and you can observe magnetic fields either by, say, synchrotron radiation, which maybe astronomers are pretty close, right? They'll figure out ways of observing this. But there are signals that you can detect in the presence of magnetic field. And so, in principle, if you can detect these things, you can get insights into the dynamics of these extrasolar planets, tell you something about what's going on the inside from an observation that you make light years away, which is amazing, actually, if it works out.
Okay, let's move on to a slightly more general conversation. Maybe Michael wants to join us on stage.